This is a Physics Edexcel GCSE paper, higher tier, paper 2 from June 21. A student gives a plastic strip an overall charge. Describe one way that the student can give the plastic strip an overall charge by rubbing it, so through use of friction. Figure 1 shows a gold leaf electroscope that can be used to investigate static electricity. The electroscope has no overall charge. The gold leaf has a very small mass and can bend very easily. The student brings a negatively charged plastic strip near to the cap of the electroscope. The gold leaf bends away from the metal rod. Which diagram shows the way that the electric charge is now distributed? C is the answer. Let's try and understand why. So think about what's happening here, in that we know that the positive ions can't move, only electrons are free to move. This plastic strip is negatively charged, which means that the negative electrons which were here would be repelled, hence why they've moved down here. Figure 2a shows another gold leaf electroscope that has been given an overall negative charge. A student connects a metal cap to the charged electroscope to earth with a piece of wire as shown in 2b. Explain why the gold leaf has moved. Well, because we have this earthing strip over here, it means those excess electrons flow down here, meaning that the gold leaf has been discharged and therefore it's no longer repelled. Two small objects P and Q are each given an electric charge. Use information from figure 3 to give two differences between the charge on P and the charge on Q. First of all, look at the direction of the arrows. We can point out that the charge on P is opposite to the charge on Q. And then secondly, look at how close together these arrows are. They're closer on Q, meaning that the charge is greater on Q. Object P and object Q are held near to each other so that their electric fields interact with each other. State the effect that the electric field of object Q has on object P. Well, we know that the charges are in opposite directions, so what you'll find is that there's a force of attraction on object P from object Q. Figure 4 shows the results from an experiment where the potential difference voltage across the filament lamp was varied. The current and voltage were measured. Describe the relationship between the current and the voltage as shown in the graph in figure 4. Well, we can see that there's a positive correlation between the two, so as voltage increases, current increases. However, it's a non-linear relationship. Despite the fact that it does pass through zero, it's not directly proportional, and that's because of this non-linear curved graph line. Use the values of the voltage and current at point P and point Q on the graph in figure 4 to complete the table. So let's look at P. We can see the voltage is 1 and the current is 20. What about at point Q? I'd say that the voltage here is 3.5 and the current is around 43. Calculate the resistance of the filament lamp when the voltage is 4.5 volts and the current is 51 milliamps. Use this equation. We've got a standard SI unit of ohms there, so we need to get milliamps into amps by dividing by 1000. So that's 0.051 amps. Do sort out your units to avoid losing any marks. So our answer here is 88.2. Explain why the resistance of the filament lamp changes as the voltage across it increases. First of all, let's make a decision as to what's going to happen while the resistance is going to increase. And why is that? Well, as the voltage increases, the temperature increases, and that causes vibrations of metal ions within that filament lamp, which inhibits the flow of electrons. Describe in terms of particles two differences between a solid and a liquid of the same substance. Well, first of all, in a solid, particles are closer together. And in a solid, particles are held in a regular arrangement or in a fixed position. In a liquid, they move randomly. Figure 6 shows the dimensions of a solid block of concrete. Density of the concrete is this value. Calculate the mass of the concrete block and use this equation. So our density is 2,100. And then we need our volume. So we do length times width times height to get 0.3. So our value for mass is 630 kilograms. Figure 7 shows a shed mostly made of concrete blocks. State two practical ways to reduce heat loss from this shed. Let's add cavity wall insulation, because that gap will have air, which is a good insulator, or if you're feeling pro, you could add foam, which would reduce convection currents. We can see that it has a window. We don't know anything about the window, but I'm going to say use double glazed windows for the same reason as the cavity wall insulation. You could have also said use cladding, use a reflective paint, close the window or the door. On a very cold day, the temperature of the air is -4 degrees. Calculate the value of this temperature on the Kelvin scale. So we add 273. And so -4 plus 273 is 269 Kelvin. Figure 8 shows some water in a tank. The bottom of the tank has an area of 0.8 meters squared. The force on the bottom of the tank due to water is 2,400 newtons. Calculate the pressure. So we need this formula triangle, which states that pressure is force over area. The force is 2,400 newtons. Our area is 0.8. So our answer is 3,000 pascals. More water is added to the tank. Explain how the pressure on the bottom of the tank changes when more water is added to the tank. So first we'll state that that pressure increases. Why is that? Because there's greater force due to water. Figure 9 shows an object on the bottom of the tank of water. Draw an arrow on figure 9 to show the direction of the force exerted by the water on the surface of the object at point X. So you need an arrow which looks like this. So it's occurring perpendicular to that object's surface. Figure 10 is a graph showing how the atmospheric pressure changes with height above sea level. An aeroplane descends from 6,000 meters to 2,000 meters. Use the graph to find the change in atmospheric pressure as the aeroplane descends. So we'll draw some lines on our graph at 6,000 meters and 2,000 meters, and then read across to our y-axis. And so the difference between these two numbers is 30 kPa. Suggests one reason why the atmospheric pressure is greater at 2,000 meters than at 6,000 meters. For me, the most straightforward answer here is it's going to be hotter. The higher temperature at 2,000 meters. We know that as we go higher altitude, up high mountains, it gets colder. And that would explain, because those particles are vibrating more, why the pressure is greater at a lower altitude. Figure 11 shows two drawings of the same person on a bed. Explain why the person exerts a different pressure on the bed when standing up than lying down. Again, let's point out what that change in pressure is. So standing up, a higher pressure is exerted. Why? Because they have a smaller area in contact with the bed. Look, it's just their feet as opposed to their whole legs and back. And then always state an equation, pressure equals force over area. So you can clearly see, even if their weight stays the same, their force, if that area decreases, pressure increases. A student uses plotting compasses to investigate the magnetic field between the poles of two bar magnets. Figure 12 shows one of the plotting compasses and one of the bar magnets. The student places the two bar magnets on a piece of paper with a pole of one magnet a few centimetres away from the pole of the other. The student places 20 plotting compasses on the paper near the magnets. Figure 13 shows the direction in which each of the plotting compasses points. Draw two rectangles on figure 13 to show the positions of these two bar magnets. Label the North Pole and the South Pole. Okay, this one's quite hard. So you might have seen these sorts of diagrams before. North, South. And if you have this sort of setup, remember that the magnetic field lines always flow like this. From north to south, so like this. And that if you were to place plotting compasses in these positions, they'd be pointing in the direction that these arrows are pointing. So you have to try and work out what must be going on here in order to get this situation. And this arises when you have actually two of the same pole pointing towards each other. And to work out which pole it is, it's going to be the South Pole, because look, the arrow always points to the South Pole. So that's why I know that this is the South Pole, and they're actually repelling. Sorry, this is really poorly drawn. But if you were to actually draw those magnetic field lines as a complete circle, remember they'd circle back like this. But the fact that we don't have that direction where they are pointing north to south means that we have a repulsion going on. The student wants to determine the shape of the magnetic field for a larger area around the magnets. Describe how the student should continue the investigation using just one plotting compass. So not too complicated here. You want to place a plotting compass on the paper near the magnets and put a dot to show which direction that plotting compass arrow is pointing. And then we just move that compass slightly so that one end of its needle is over the mark that you've just made. And as you can see, you'll end up with a join the dot situation. Two long thin magnets are held with their north poles facing each other. The force F between the magnets can be calculated using this equation, where K is a constant value, D is the distance between the magnets. The magnets are 4 centimetres apart, which is the same as 0.04 metres. Always being careful with units. The force between the magnets is 1.2 newtons. Calculate the value of K and state the unit. So we're using this equation. Our force is 1.2 newtons. We're after K and our distance is 0.04, which we need to square. So do 0.04 squared and then multiply it by 1.2 to find the value of K. So K equals 1.92 times 10 to the minus 3. What would the unit be? Well, if we rearrange this formula to find K, it's FD squared, so that will be Newton meters squared. The magnets are held the same distance apart, but with the north pole of one magnet now facing the S pole of the other magnet. The value k does not change. State how the force would compare with the force in part 1. Because you've switched the poles, you'd find that the force would be acting in the opposite direction, but that the value of that force would remain the same, so its magnitude remains the same. A student investigates moments of forces. Figure 14 shows the apparatus used. The pivot is under the centre of the rod. The magnet is fixed to one end of the rod. A piece of modelling clay is fixed to the other end. The system is in equilibrium. State the relationship between the moment of the weight of the magnet and the moment of the weight of the modelling clay about the pivot. Clockwise moment equals anti-clockwise moment. That is the principle of moments. The student fixes a coil to the bench under the magnet as shown in figure 15. The coil of wire is connected to a direct current power supply so that there is current in the coil. To bring the system back into equilibrium, the student hangs a 0.05 Newton weight on the rod, 8.4 centimetres away from the pivot as shown. Calculate the size of the force between the magnet and the coil. So that's 0.084 metres. So we're going to write clockwise moment equals anti-clockwise moment. So what about our clockwise moment? So it's this side. So remember, moment is force times distance. So we're going to do 0.084 as the distance times by the weight, or that force, which is 0.05, equals, we've got the distance for the anti-clockwise moment, it's 0.12, times the force which we're after. So work out the left-hand side by doing 0.084 multiplied by 0.05. So that's 4.2 times 10 to the minus 3 equals 0.12x. So divide 4.2 times 10 to the minus 3 by 0.12. So our force is 0.035 newtons. Describe how the student could develop the investigation to determine if the size of the force between the magnet and the coil is directly proportional to the size of the current in the coil. So if we think about what we're trying to prove, which is that this relationship is directly proportional, it means that we'd plot a graph of force against current, and that graph line would pass through the origin and be straight, hence it would be directly proportional. But we're trying to develop the investigation, so we need an independent variable, and that will be the current. Use a range of values. Our dependent variable, what we're measuring, is the force. And then plot a graph of force against current. A directly proportional relationship would pass through the origin. The student reverses the direction of the current in the coil. Describe how the student can bring the system back into equilibrium without making any changes to the magnet. Let's have a look at the diagram to make sure we know what's going on. So before we reverse the direction of the current, we know that that magnet is being attracted downwards. However, because the current has switched, that has the knock-on effect of meaning that the magnet is effectively pushed away from that coil of wire, bringing down this side of our bench. So the only way we can stop that is by adding weight to this side of the pivot, because that will mean that the magnet comes down again without having to make any changes to the magnet. So we're adding weight between the pivot and magnet really to get those 2 marks. 2 cyclists ride on a hilly road and go through points P, Q, R and S. The diagram in figure 16 shows how the vertical height of the road changes during the journey. The greatest overall change in gravitational potential energy for each cyclist is between which 2 points on the journey. So we need to decide where the greatest change in height occurs, and that's between R and S. So D. The total weight of one cyclist and the bike is 700 newtons. Calculate the total amount of work done against gravity when the cyclist travels from point P to point Q of the journey. So what's our height difference there? 20 meters. So work done, remember, is force times distance. Our force is 700 because remember force and weight have the same unit. Our distance is 20 meters, so our final answer is 14,000 joules. The gravitational potential energy of the other cyclist changes by 11,250 joules when travelling from point Q to point R. From here to here. Calculate the mass of this cyclist using this equation. So what is that height difference? It's 15. G we're told is 10. We're after our mass and we know the change in energy is 11,250. So sort out the right hand side becomes 150 m. Divide both sides by 150 to find m to get a very sensible mass of 75 kilos. Explain why the total amount of work done by a cyclist between points Q and R is different from the change in gravitational potential energy of the cyclist between Q and R. Yeah, because usually we say these values are the same, so we need to work out where energy is lost. So first of all, some work is done to overcome friction or air resistance, and lots of energy is dissipated to the surroundings, potentially as thermal energy. The cyclists lubricated the chains and the wheel bearings of their bicycles before setting off. Lubricating the chains and wheel bearings helps to... It's going to be all about reducing the friction between these things, which will increase the efficiency overall of the cyclist and the bicycle. The kinetic energy of another cyclist is 2,800 joules. The mass is 85 kilos. Calculate the velocity. So 2,800 is our energy, our kinetic energy. We're doing half of their mass, which is 85 kilos. We're after V. Sort out your right hand side first of all. So 85 divided by 2 is 42.5 times V squared. Divide both sides by 42.5 to get 65.882. And then finally square root your answer to find V, which is 8.12. A technician investigates different electrical devices that are used in a car. The technician connects the device to the 12-volt car battery. The technician measures the current in the circuit and the potential difference across the device. Figure 17 shows the car battery and the device that's being tested. Draw on figure 17 to show how the circuit should be completed so that the current in the circuit and the voltage across the device can be measured. Remember that a voltmeter is always added in parallel. And then the ammeter is always added in series. The technician tests a headlamp. The current in the headlamp is 4.8 amps. When connected to a 12-volt battery, calculate the power supplied. So we want this equation, which states that power is current times voltage. 57.6 watts is our answer. The technician tests an interior light. The current in the interior light is 600 milliamps when connected to the 12-volt battery. Calculate the energy transferred in 7 minutes. So let's get this into amps by dividing by 1,000. We need this equation, which states that energy is current. So there's our current value, times voltage, times time. Be careful, we need that in seconds by timesing by 60. Just run that all into your calculator to get 3,024. The technician connects 4 devices to the car battery. Each device is connected to its own switch and its own fuse. Figure 18 shows how the 4 devices, fuses and switches are connected. The current in each device is shown next to the device. Calculate the current in the wires to the battery when all devices are switched on. So we really just need to add these all up. Just be careful with your units again. These are all in amps. This one is in milliamps, so again, divide it by 1,000. So what you're doing is 4.8 plus 600 over 1,000 plus 10 plus 2.3 to get 17.16. State how the overall resistance of the circuit changes when one of the devices is switched off. So if that switch is effectively opened, it means that the current will only flow down the other routes, and therefore the resistance increases as the electrons have fewer routes to pass along. There is a current of 2.3 amps in the radio when the radio is working correctly. Which of these should the technician choose to protect the radio circuit? You need a fuse with a current rating slightly higher than the current flowing. So this one's too low, and this one's just about right, and these are too high. Explain why the wires to the battery in a car are thicker than the wires that connect each device to its switch and its fuse. Now, when a wire is thicker, it has lower resistance, because remember, the wider the diameter, the lower the resistance, and that therefore means that there's less of a heating effect. The wires don't get hot, meaning that more current can be carried or less voltage is lost. There is an alternating current of 3 amps in the primary coil of a transformer. There is an alternating current of 6 amps in the secondary coil. The transformer is 100% efficient. The size of the potential difference voltage across the secondary coil is, remember the equation goes current primary times voltage primary equals current secondary times voltage secondary. So let's sub in what we know. We know that these values are equal because the transformer is 100% efficient. So let's say the total value on each side was 6, then that would mean that voltage primary had to be 2 and voltage secondary had to be 1. And if you look down at these options, we can see that the voltage is double that across the primary coil compared with the secondary coil. So what makes sense here is that the voltage across the secondary coil is half that across the primary coil. Explain how an alternating current in the primary coil causes an alternating current in the secondary coil. So remember that there is a alternating magnetic field set up across the primary coil. This magnetic field cuts the secondary coil, therefore inducing an alternating voltage across the secondary coil. The primary coil of a different transformer is connected to the 230 volts main supply. The voltage across the secondary coil is 15 volts. The primary coil has 600 turns. Calculate the number of turns on the secondary coil. You need this equation. And then just substitute everything in the right place. So our voltage primary is 230. Voltage secondary is 15 volts. Primary coil has 600 turns, and we're after number of turns on the secondary coil. So first of all, work out 230 divided by 15. And then how to solve for x, cross multiply so it looks like this to get 39.1 as your answer. So 39 because you need a complete number of turns. Figure 19 shows a coil of wire that is being rotated between the poles of a magnet. Figure 20 shows how the current in the coil changes during one complete rotation of the coil. Explain why the current changes in the way shown by the graph in figure 20. Your answer should include details of the position of the coil relative to the magnet at each of the times labelled P, Q, R, S and T. You may use diagrams in your answer. So this is the generator effect, and what happens is when you move that coil of wire inside a magnetic field, it creates a voltage, which when it's part of a main circuit like this is, creates a current, which is alternating. So we're first of all going to talk about how that generator effect comes about. So the coil moving cuts through the magnetic field. inducing both a voltage and current in the coil. Now the size of that current will depend on the rate of change of the magnetic field. Now that rate of change will be greatest when the coil is moving at right angles to the magnetic field, or perpendicular if you're feeling fancy. And so if we think about what we've just said, that the greatest rate of change occurs when the coil is moving perpendicular to the field, we can therefore understand that where the current is at its greatest, so that's both Q and S, that must mean that the coil is horizontal. And then if we look down here where current is 0, that must mean that the coil is held in a vertical position. So let's check how many marking points we have. The coil moving cuts through the magnetic field is 1 mark. Inducing the voltage current is a 2nd mark. The size of the current depends on the rate of change of the magnetic field is a 3rd mark. The greatest rate of change occurs when the coil is moving perpendicular is a 4th mark. And then these points here, that maximum current is at Q and S. Current is 0 at P, R and T. They're additional marks, and then the explanation is more marks as well. So we've definitely reached our 6 marks. An electric kettle contains 1.41 kilograms of water at 25 degrees. The kettle is switched on, and after a while the water reaches a boiling point of 100 degrees. The specific heat capacity is this. Calculate the amount of thermal energy supplied. Give your answer to an appropriate number of significant figures. So we need Q equals MC delta T. Q is what we're after. There's our mass. Here's our specific heat capacity. And our change in temperature is the difference between these two numbers, so 75 degrees. So do label all these numbers to make it as straightforward as possible for yourself. Put that into your calculator. And then the minimum number of significant figures we've been given is 2, so I'm going to choose 2 significant figures here. The kettle is kept switched on and the water continues to boil. After a while, the mass of the water in the kettle has decreased by 1.21 kilograms. So we actually only have 0.2 kilograms left compared with our original amount. The thermal energy supplied to the water during this time was this. Calculate the specific latent heat of vaporization. So we want energy equals mL. We know E is 450,000. Our mass is 0.2. We're after L. So divide both sides by 0.2 to get 225,123,4 zeros as our answer. This question is about determining the specific heat capacity of aluminium. An aluminium block is placed in boiling water as shown. The piece of string is tied to the aluminium block so the block can be transferred from the boiling water to the cold water. Describe how a student could use this apparatus and any additional items needed to determine the specific heat capacity of aluminium. Your answer should include how the student would obtain necessary measurements and use these measurements to calculate the specific heat capacity of aluminium. In order to do this, let's look at this equation. And let's rearrange it. So we know that specific heat capacity is energy transferred divided by mass times the temperature change. So we need ways of determining these numbers. So clearly we'll need a mass value, and remember what we're doing is by heating that aluminium, we're increasing the temperature of the water, so it's always in these calculations the mass of the water that we're interested in. So let's first of all talk about how we're going to find the mass of the water. So measure the mass of beaker water and aluminium using a balance. Always state appropriate apparatus. Empty the water from the beaker and dry the beaker and block. Find mass of beaker and block alone. Take this value away from original value to find the mass of water. So we're finally there with the water's mass. Let's talk about this change in temperature now. So find change in temperature by finding the temperature of water before and after heating using a thermometer. And then we know that the specific heat capacity of water is this. So use, because you now have all the values you need to find E, so energy transferred for water. And remember that the thermal energy gained by the water is the same as the thermal energy lost by aluminium, which means you now have enough info to use that original equation, which remember was this, C equals E, because remember you can measure the mass of aluminium using that balance, and you can write that out too if you want. We know E is the same as what we just calculated for water. We can calculate the temperature change for aluminium by subtracting the final temperature from 100, and then by doing all of that we can then find C. You know what, 6 marks, I think I've said like 10 marks worth of stuff. I don't really like this question because A, I don't have very much space to write. I know there's more lines below, but personally I feel like I should have gotten everything I needed in here. And obviously there's a lot of toing and froing using this equation, first of all to find E for water and then subbing it in to find the specific heat capacity for aluminium. So I think there's an awful lot in the method that we could have added to add an extra like 4 or 5 extra marks to give this the full answer it requires.